let's work through some examples using differential equations. The first and most common is probably the growth and decay model, and I expect you're probably familiar with that. You've probably seen it back in a college algebra course where you had a formula like y equals the ce to the kt, which modeled growth or decay for certain items. C being an initial population size, K being a growth constant, T being an amount of time, Y is a function of T, so the new population size is decided based off the current value of T, and E, of course, is the base of the natural logarithm. So let's take a look how this is derived, because I don't think that anybody started with this as a particular model. Let's see where we can possibly come up with this. So the basic idea behind population growth is that the larger a population is, the faster it grows, which should make perfect sense. If you have more items in the population to reproduce, the level of reproduction at each generational stage increases. But this can be more formally stated in this way. The rate of change of the size of a population is proportional to the current size of the population. So that means basically the same thing, the rate of change of the population, so that's the increase or decrease in the size of the population, but anytime we talk about rate of change, we are talking about derivatives. And if you can take a problem and work the language so that you can involve a rate of change, you know that you can involve a derivative there. So the rate of change of the size of the population is proportional to the current size of the population. So whatever the current population size is determines how quickly it's going to change. Now, proportional means kind of like equal, but not exactly. It means equal, but possibly off by a multiply constant. So let me write that in. So multiplied constant. Okay, so what we can do is we can take this statement and we can rework it into this formula right here. So dy dt represents the population, the rate of change of the population size, because the population size is the variable y, and we're looking at how it changes over time. K is a constant of proportionality, and y is the current population size. So this is actually a little bit easier to develop as a formula in terms of developing a model for growth. Because what we can do then is we can solve this model for the function y. And the way we would do that is through the separation of variables. So let's give it a try. Let's solve this and see what happens. So if I solve this, the one thing that I'm going to need to do first is separate my variables. And to get that done, the first thing I would do is move the dt to the other side. But anytime I have a function involving a variable that's not matching the derivatives variable, I need to move it to the other side. So this y right here needs to come to this side. So this would be 1 over y dy is equal to k dt. So now I have my variables separated. And the next thing I would do once I separate my variables in order to solve a differential equation is to integrate both sides with respect to the variable given. So when I integrate 1 over y with respect to y, that's a natural logarithm. So the natural log of the absolute value of y. And integrating a constant, that just ends up being the constant itself times the variable of integration, and then this could be plus some arbitrary constant c. And that's one way of expressing the solution, but it would be nice if we could get this solved for y. So what we'll do next here is effectively raise each side of this equation as if it's an exponent with a base matching this logarithm's base. So let's do that. Okay, and when I do that, whenever I take an exponential function, raise it to a logarithm of the same base, there's a rule that says this just reduces down to the variable that is in the argument of the logarithm. So this becomes just y on the left-hand side. And I suppose technically I should say the absolute value of y, but let's assume that our population size, since we're dealing with an application of counting real units of items, that we would never really have a negative population anyway, so let's just ignore the absolute value. And that's now equal to e to the kt, and then anytime we have something that's added inside of an exponent, we can actually split that up into two exponential functions with the same bases that are multiplied. And here's kind of a neat thing again with differential equations. E to an arbitrary constant is just as arbitrary as the variable c itself. So I could really write this as y equals ce to the kt, and that is the standard growth and decay model that we showed just a second ago. So our standard growth and decay model. And you're going to run into some questions similar to earlier classes where you would have to answer questions based off the standard growth and decay model. But now that it's developed, you don't necessarily have to do the step of deriving it first. You can always just start with that model if that's what the example requires. Now, occasionally you might run into a situation where another form of a growth model is useful, and that's y equals c times some value p raised to t. And this isn't, this is more of a discrete model, but if you have the percent change per unit time, you can use that percent change here as opposed to like having e to the k times t. It's generally an easier model to work with, but it's more common, I think, to use the standard growth and decay model. But if you see a situation where you can use it, it certainly is easier. Let's work with examples using the standard growth model. Now, there are some pretty common examples that we run into here. Certainly, we've already talked about population growth, and the idea is that, at least over a short period, populations are assumed to grow exponentially, neglecting any external factors. So like if a terrible storm comes in and forces people to flee a particular city, well, the growth model isn't going to account for that. So half-life, that's another example where the standard growth model is very useful. And the idea there is radioactive materials, they decay in such a way that half the material decays into other elements over a specific amount of time, and that's very measurable and precise, and so you can use this model to make predictions based off of those types of questions. Compounding interest, or I guess I should say continuously compounding interest, is the one that runs into the standard growth model. You may have run into examples with this in previous courses, but I wouldn't expect many here. Then also Newton's law of cooling. And Newton's law of cooling is actually a little bit more advanced. We would need to resolve a new differential equation to come up with a solution using Newton's law of cooling. But it's just one more step in advancement. It actually just adds an additional constant to the equation, and it's kind of interesting to see how that makes the problem play out. We'll do an example of that one later on. So for now, let's just kind of focus on the first two here. So this example here, predict the population of the US in 2020 if the reported population during the 1990 census was 248,200,000, and 281,400,000 and 2,000. And no, I'm not going to update this question for new numbers. Clearly it's in the past. But you can now go back on Wikipedia and check and see if the number predicted was correct. That might be fun. Okay, so let's see what we do here. So working any kind of a word problem, it's best to keep in mind what it is you're trying to figure out. Because if you just kind of jump into formulas, you might understand the situation enough to actually work it through, but you can change the parameters only slightly and it might not make quite so much sense. So you really just need to kind of focus on what it is you're trying to do, what you can use to get there, and let the mathematics walk you through. So our goal here, our goal in this question is to predict the population size in 2020. Okay, so let's keep that in mind. And it's also great to identify variables. So what kinds of things are we observing changes of? So certainly we have the population size, and we'll just note the population size to be the variable y. But then we also have time. So time is changing through this example, so we'll give that a letter t. And we have our growth model. If we didn't have this to start with, we would spend a little time developing some sort of model to work this out for us, but here we have it, y equals ce to the kt. And C, of course, is an initial population size. And K is a growth constant. Okay, now if we knew what the growth constant was, we could already make a prediction of the population size in 2020, because technically the initial population size, one little trick we can do here is we can basically say that instead of using, like, we can set up coordinate pairs, for instance, using our variables t and y. So we can say, instead of in time 2000, we can say at time 0, just set 2000 to t equals 0. We know the population size to be, I'm not going to write all those zeros, let's say, I'm sorry, 1990 should be t equals 0. This would be t equals 10 years later. All right, but I'm still not writing all the zeros for the other value, so 248.2. I'm just going to slide the decimal a few places for simplicity. And then my answer, of course, would just be, in millions, that's all. And then we know 10 years later, the population size is 281.4. And then what we want to know is, in 2020, so when t equals 20, what is this population size? So we need some model to help us determine that. And when it comes to, and actually, I was thinking this to be from 2000 again, so 30 years down the road would be 2020. All right, so when working with a model like this, what we need to do is basically just feed it information, okay? Because what's happening behind the scenes, let me draw a little sketch here. All right, so we have a couple of points, and I'm going to label this 0, even though that's weird because this should be 0 here, but just bear with me. 0, 10, and that would be 20, so this would be 30. Okay, and let's see, how can I break this down easily? Let's just say 240, 250, 260, 270, and 280. That'll work fine. And then that's a bit of a broken scale there. Okay, so I have one data point, 0, 248, so it's like right there. The next data point is 10, 281.4, which is way up here. And then 30, it's going to be, clearly higher. I guess I should have scaled this a bit differently, but the idea is there's going to be some exponential function which fits through this model. And our goal is to figure out what is this exponential function so that we can use that to make a prediction as to what the population size would be in 30 years down the road. So we need an exponential function that fits through these 2 points. So we're going to take this general exponential function and do just that, just fit it through those 2 points. So if we want it to fit through the first point, here's what we would do. We would just take the point 0, 248.2 and just plug it in. Remember, this is a variable t and this is the variable y, so we would have y equals ce to the k times t, which is 0. And of course, y can be replaced with 248.2. Well, what happens? So e to the k times 0, so that would just be 0, or e to the 0th power. Anything to the 0th power is just 1. So that ultimately leads us to determining the value of our initial population size, which is 248.2, which is not entirely groundbreaking. We actually kind of knew that because when t equals 0, that's the initial population size. But, the model told us that as well. That's good. Now we have this other point. We have 10 and 281.4. So this is a y value. So I could say 281.4 equals my model. My model now looks like c, which is known to be 248.2, e to the k times this new t value, 10. And let's see what happens. So I could divide both sides by 248.2. And I generally don't actually divide these until I absolutely have to, just because you'll end up having to round. And the thing is, most instructors won't take off a rounding error, especially if you have your work supporting what you're doing. But the homework systems aren't always so easy about early rounding, so just leave that open. And then that's now equal to e to the 10k, which I could change into a logarithm. And if I change that into a logarithm, it would look like a natural log of this thing is equal to the exponent 10 times k. If you're not sure how to go from exponential form of an equation to logarithmic form, let your instructor know and get some more advice on that. But that's definitely something from earlier courses. But get some advice if you need it. And then we can solve for k just by dividing by 10. So this would be the natural log of all of this business divided by 10. All right, so we can use the calculator to help us determine that value. And let me bring that up for us here. Give me 1 second. Okay, so natural log of 281.4. Then inside this parentheses, divide by 248.2. Then close your parentheses, because that's the end of the logarithm part. Then we have to divide by 10. All right, so 0.01255. Okay, so that figures out the growth constant. So now our growth model looks like y equals 248.2 e to the 0.01255 t. And I can figure out what the population size should be at any particular point in time simply by plugging into that formula. So if I want to know what it is 30 years down the road, it would be 248.2 e to the 0.01255 times 30. And that again is something that we would just plug into the calculator. Now, here's something you're going to want to get used to. I have written 0.01255 down here because it's easier to write, 5 numbers instead of, I guess, 9 or 12, something like that, however many decimals is shown here. But when you go to work these problems in the homework, you want it to be as accurate as possible. So just know that this number is this one over here. And then work with this one on the calculator. And it's actually fairly easy to do. Like, here's what I need to do. I need to multiply that number by 30. So let's just, if you hit multiply, it takes the previous answer and multiplies that by 30. Now I'm taking this exact figure, dividing by that. So a little bit more accurate. Then take e raised to that result and multiply it ultimately by 248.2. Now you're safe to do some sort of rounding if you need to, and that way you ensure to get the most accurate answer you can. So let's say 361.7, or of course 361,700,000 would be the predicted population size in 2020. Okay, now let's take a look at an example using half-life. So here we have the half-life of carbon-14 is 5,730 years. Find the amount of time it will take 20 grams of carbon-14 to decay to 3 grams. Well, let's see what's needed here. All right, so if you want to estimate what the answer is going to be, here's something you could kind of do. So to start, well, let's just say amount and time. All right, so this is the variable y, and this is the variable t. So at time equals 0, we start with 20 grams. All right, then 5,730 years down the line, once that passes, half of the amount has decayed away. So now we're down to 10 grams. Another 5,730 years, which 11,460. I should probably check that. So 5,730 times 2. Hey, not bad. All right. Once that number of years passes, we're down to 5 grams. All right. Another 5,730 years passes. So yeah, I'm going to actually just come over here. Times 3. So 17,190. Now it's down to 2.5 grams. So we're looking for 3 grams, which is somewhere within this range. So, what is this value here? What's that amount of time? Well, it's somewhere between 11,000 and 17,000 years, but let's see if we can get any more accurate of a response. Okay, so our growth model starts out looking like y equals ce to the kt, but we actually already know the value of c. We have this initial amount of 20 grams. So let's just plug that in and not worry about it. And then we have this point next here that there's 10 grams remaining after 5,730 years. So there's 10 grams left once we let the time pass to 5,730. When I divide by 20 to get the exponential by itself, that gives me 1/2 on this side equals e to the 5,730 times k. And if I change this into a logarithm, it would be a log base e, so a natural log, of 1/2 equals that exponent. And then just divide through by the exponent, so k would be the natural log of 1/2 divided by 5,730. And when I do that in the calculator, so natural log of 0.5 divided by 5,730, I get this, which is just scientific notation, of course. So let's see, 3 leading zeros, so negative 0.000121. Did I round that properly? Yeah, that's fine, 121. Ultimately, I'm not going to use a rounded value when I start doing some calculations with it, but I'll just write it this way for simplicity. Okay, so now my model looks like y equals 20 e to the negative 0.000121 t. And with that, I can now predict, how much time it takes to reach a particular amount remaining. But unlike the previous example, where once I got this model, I plugged in a value here for t, I'm going to plug in a value here for y, because I'm solving for how long it takes to reach population size, or an amount remaining, however you want to look at that. So the new amount I want is 3 grams. Then if I divide both sides by 20, that cancels out. And I have 3 divided by 20 equals e to the negative 0.000121 t. And I can't solve an exponential that has a variable in the exponent, so I need to switch into logarithmic form. So a log base e, which would be a natural logarithm of this side of the equation, 3e over 20, would be equal to the exponent. And then t, I can now determine by taking the natural log of 3 over 20 divided by negative 0.000121, and let's see what we get here on the calculator. So let me just clear that, I suppose. All right, natural log of 3 divided by 20, and then I'm going to divide by this number, but it's actually still saved as the previous answer. That's the last number we came up with, so I'm going to use that. And I get 15,683 years. I'll just go to the nearest year here. So 15,683 years. And that is right in line. Certainly the 3 grams was closer to the 2.5 than it was the 5. And likewise, the 15,683 is closer to the 17 than it is to the 11. So this checks out. This actually makes a lot of sense with our initial prediction. And those are some of the types of problems that you're going to be required to be able to do. So get some practice with those in the homework, and then start the remaining video.